Okay, so today basically in this lecture, I'll cover some of the basic techniques that you've been hearing about the transmission spectroscopy and the emission spectroscopy. First, I'll go to the motivation of why that is important and how do you use, and then I'll going to derive some equations, basically radio transfer equations, like how do we compute using models this transmission spectra so that we can interpret the observations of exoplanet atmospheres that we are receiving with JWST, HST, various different telescopes. So that will be the main focus of today's lecture. So in many of the talks you have been listening, like we have detected exoplanets. So what next? So what comes in your mind once we have found the planet? What do we have to do next? Yeah, speak up, yeah. Go ahead. Atmospheric characterization. What else? What comes within that atmospheric characterization? Okay, rocky planet or a gas giant, yes. Then what else? Thermal radiation. Temperature, yes, correct. Temperature, structure, correct. So all these things are very important questions that we have to answer from if you want to understand exoplanet fully. So like, does it have an atmosphere? That's the first question we need to answer. Then are there any clouds or haze? What is its atmospheric composition? And what is its interior composition? So all these questions are together connected. And once we detect exoplanets, all this information, getting this information is very difficult. I'll tell you why. We'll do some calculations, and that is the reason that it becomes challenging. And we have only access to the atmosphere to get to the deeper parts, understanding the deeper parts of the planet as well. And that is why we have to understand the atmosphere and characterize it very well to do this. So now with more than 5,000 exoplanets, we have a wide range of planets and possibly their atmosphere. Because if we look at our solar system itself, we have Earth with nitrogen dominated atmosphere, we have Mars with carbon dioxide dominated atmosphere, Venus again with CO2 dominated atmosphere but very high pressure with sulfuric acid cloud, Titan, Jupiter, Saturn, Neptune, each with different types of atmosphere. There are different gases. So just with these 8 planets, we can see that so much variety exists just in the type of atmospheres these planets can have. So imagine for exoplanets where there is much more diversity because they are around different kinds of stars. Exoplanets are around different, like there are M type, G type, there can be around different types of stars. They can be at different distances from their host star. Their formation mechanisms can be different. Their initial abundances when they form can be different. So all these different things can lead to a wide range of exoplanet atmospheres that can form around these planets that we have detected. So that is also one of the main motivation, like what is the diversity that we'll find out. So we have just begun to scratch the surface with the observations that we have. Then another important thing about the atmosphere is the atmosphere is very important for life. And this we see for Earth. Like this is the Earth, the atmosphere is very small, like basically 100 kilometers compared to the total radius of the Earth. But because of the presence of the atmosphere, we have the greenhouse effect that happens and that makes life possible on Earth. Because without greenhouse effect, the Earth's temperature, the equilibrium temperature would have been 255 Kelvin. It is because of this additional 33 Kelvin addition, we get a environment where life can flourish. So it is because of this atmosphere that is possible. So that's why if we are searching for habitable planets as well, we have to understand its atmosphere and characterize it. And why atmosphere is important for habitability, we have a lesson from our solar system itself. As I was mentioning, Earth is like equilibrium temperature 255 Kelvin, actual surface temperature 288 Kelvin. But if you look at Venus, its equilibrium temperature is 260 Kelvin. So equilibrium temperature is the temperature based that can be calculated based on the distance of the planets from its host star. So it does not include any information about the atmosphere of the planet except the albedo. So, but the actual surface temperature of Venus is 700 Kelvin. So why such a big difference? So this basically the big difference is the atmospheric composition. A CO2 dominated atmosphere in Venus basically leads to extreme greenhouse effect. We call it a runaway greenhouse effect. And that leads to a very high temperature, which makes life difficult to evolve. Yeah, there are theories that maybe at some point of time, Venus was habitable and its temperature was lower, but it's still debatable although. So the main thing to take away is this atmosphere plays a very, very important role in determining the habitability of the planet. So that leads to what are the big questions that we need to answer? based on all the things that I have shown in the previous 2-3 slides. So what is the diversity in exoplanet atmosphere? That is important. We have to learn and understand that. How do exoplanets and their atmospheres form and evolve? What are the fundamental physical and chemical processes that shape different exoplanet atmospheres? What makes Earth habitable, and was it always like this? That's also an important question. Like, is Earth unique? Basically, and was it always like that? How do we find other habitable planets in our galaxy? So unless we answer all these questions, we won't be able to, like, we have to define what habitable planets are. So how do we find them? All these things we learn when we study the atmospheres of the exoplanets and characterize them. So I hope I have given you enough motivation, like why we have to study exoplanet atmospheres. Okay. So I'll now delve into the techniques that we use to do that. So you might have heard about the transit method very frequently in the talks. So the transit method has been the most successful method to detect exoplanets. Okay. And the same method has also been the most successful one to characterize exoplanet atmosphere. So basically, as the planet goes in front of the star, there's a dip, and this dip is what we see and detect the planet. So I'll come to what we do in transmission spectroscopy in the coming slides. But I just wanted to give you an overview of how do we do exoplanet atmospheric characterization in different geometry. So in the previous slide, I showed the transit, like that was a primary transit. So suppose this is the host star and this is the planet going in front of the star. So when the planet comes in front of the star, that is when we get the primary transit. And this is when we obtain the transmission spectrum of the planet. But in this case, as Sourav was pointing out in the morning, we only get the information about the limb of the planet. So we are only able to characterize the exoplanet atmosphere of this limb. That is the information we get. So, but we need to characterize the atmosphere because if you look at Earth, Earth is not just the limb. You have different temperatures on the day side, night side, all different latitude, longitude, different basically winds are there, dynamics happen, all these things happen. So it's not sufficient to just get the information of. So then we have this other technique of the secondary eclipse, basically the emission. So as the planet goes around the star, so what we do is we take the measurements of flux just before it is like going or after it is going behind the star. So we get in this geometry, we get the radiation from the star plus the planet. Okay. And when the planet goes behind the star, we get just the star. So it's like simple planet plus star minus the star. So what we get is the information of the planet. And that is what basically the secondary eclipse is. I'll go into the more details of this when we delve into the model. And in the same geometry, we can also get the information of the reflection from the planet. Because it's the star, some amount of the starlight that is coming on the planet is also reflected. Because in this geometry, suppose I'm looking from here, from the Earth. So in this geometry, I'm getting the radiation from the planet, which is the emission from the planet, plus the reflection of the star. So we are getting both emission and reflection in this geometry. Okay, and here one thing I'm just making it like when we say day side, because we are assuming the planet is tidally locked. And for the close-in planets, for many of the hot Jupiter and warm Neptune, that is true. So in that case, we get basically the emission spectra and reflection spectra of the planet, which can give information basically of the day side of the planet. And in this case, we can get the information basically of the limb of the planet's planet. And also night side emission. But until JWST, this was very difficult. Very recently, we have been able to do that because your signal to noise ratio is very less because the night side temperatures are low compared to the day. Okay, so I have just given you primer to this. I'll come back again on like how do we do. And so in realistic, how do your observations look like? So this is how our, so that was the illustrative diagram. But real observation, this is from TESS. So from TESS, if you see, this is for one of the ultra hot Jupiter exoplanets, what it was 18B. If you say that the primary eclipse is massive, because ultimately, if we want to measure the atmosphere, we need to get the transit depth, basically this depth. And that depth is dependent on the difference between the baseline and how much the dip in the flux is because of the presence of the planet. So the primary eclipse is much, much stronger than the second. You see at the secondary eclipse, so low. So the SNR that we get, we have to like zoom into this. And from this, we can see that the secondary eclipse is so low compared to the primary eclipse. And that is what we get also when we study exoplanet transmission or emission spectra. The SNR that we get in transmission spectra is much, much higher compared to that in the secondary eclipse. So secondary eclipse is much, much more challenging compared to the primary. And this is what we notice from the phase curves. And basically going ahead, then when we want to understand or derive the equations from the model to get the transmission or emissions like that, this is ultimately the quantity we want to get at. We want to compute how much is delta F or change in the flux. I'll show that again. And in this also same, like what is the change in the flux because of the presence of planet's emission. This is this minute amount we need to calculate from the model. And in this large amount is basically due to the presence of. But here you have to notice the geometries are different, as I was showing in the previous slide. So just to give you some like understanding of the numbers, we'll just understand transit depth in a bit more detail. So what is transit depth? Transit depth is basically delta F is the change in the flux during transit divided by the F out is the flux out of transit. So that quantity basically is what we give us the information about the, because that quantity will be proportional to the planet. And that ultimately is basically proportional to the radius of the planet to that of the star squared. And this is the quantity that we measure. And this is what we call as transit depth. And this is very important when we detect the planets. So transit depth for different stars. Now this is important, like, because this is a ratio of the planet and the star radii. So transit depth of a smaller planet or on a bigger star will be much smaller compared to if you take the same planet but decrease the size of the star, like essentially for M dwarf. So that is why for M dwarf, like it is like we get larger transit depth, and we say that the characterization might be easier, but apart from, of course, the TLS effect, that can be a bit problematic because the stars are M dwarfs are very active. So, but if we keep that aside, the stellar activity, smaller planets are on M dwarfs or larger planets are on M dwarfs. Both are like the best targets that you could use for characterization. But stellar activity makes it very problematic. But for a G dwarf star or the like K dwarf, here the transit depth will be much lower, but still with the activity in the stars will be lower, and that will help characterization, which I will show in the further slides. Okay, so just to get a brief understanding and get numbers, can you, like, all of you with your notebook and pen, calculate what is the transit depth of Jupiter orbiting a sun-like star and Jupiter orbiting a M dwarf with radius 0.12 R sun, and similarly you can do for Earth-like planet. So you can just, should take you 2-3 minutes. So all the constants are given, whatever you will need to do this rough calculation. So it's good to get these numbers in your head, I think. So do you get Jupiter around sun? Yeah, correct. 10⁻². But you look at Jupiter on M dwarf, massive. And that is why, like, easier to find Jupiter-like planets on an M dwarfs, of course, if they exist. But the transit depth is massive. So observationally, they are a very good target. And look at Earth around sun, 10⁻⁵. That's so low. So the transit depth is so low, and that is why it is really, really challenging to find Earth-like planets around sun-like stars. So characterize them is like we cannot even think of in the current generation of telescopes that we have. Definitely, Earth around M dwarfs is somewhat that is possible because there's almost a difference of 2 orders of magnitude. So these numbers give you a ballpark estimate of, like, what are these transit depth and what is possible with the current telescopes and what is not. That's why just a small exercise. So it's a very simple calculation. RP is square by R star squared, that will give you the transit depth. So now, since you have this understanding of the transit depth, now I'll go into what transmission spectroscopy is. So when we were calculating the transit depth with, like, TESS or Kepler, basically that is photometry. We have a massive band and we calculate the transit depth using that. But if you want to do transmission spectroscopy, you want to capture the atmospheric signals of different gases that exist in the planet's atmosphere. So we need to do spectroscopy at much, much higher resolution. And that is what we do in the transmission spectroscopy. And this basically animation nicely summarizes it. Basically, you measure now your light curves in different wavelengths. And this measurement of light curves in different wavelengths gives us the information of the atmosphere, because depending on what is present in the planet's atmosphere, the planet will look bigger or smaller. So your RP bars, the transit depth in different wavelengths will be different depending on what your atmosphere is made up of. Like if suppose a particular absorber is present like at say like 2.3 microns, and so the planet will look bigger because the atmosphere, the gases in the atmosphere has absorbed them, and the planet looks bigger. That is what the transmission spectrum will finally give us, the RP, the transit depth as a function of wave. Yeah, so this basically comes from this animation. So, but looking at this now, I have told you you have calculated the transit depth. Now, I have also told you how do we get the transmission spectrum. So, what do you think will be the best targets for transmission spectroscopy? I've already given the answer here that it's the hot Jupiter and warm Neptune. And the reason is basically because of the large scale height. Okay, the atmospheres that around hot Jupiter and warm Neptune, they tend to be hydrogen and helium dominated. And because of this, the scale height will be bigger and the atmospheres will be bigger. So we'll do one rough calculation for them in one of the slides, and from that also you'll see. And so that is why they have actually been the best targets for transmission spectroscopy over the years. So the first transmission spectroscopy that we managed to do were using the Hubble Space Telescope, and that was on hot Jupiter. And over the years, even with JWST, our first targets have been hot Jupiters and warm Neptune, because there the scale height of the atmosphere is large, so which makes it possible to characterize them. And also the other reason is because they are tidally locked, so we can get the information of the day side of the atmosphere using their emission spectrum. So these all things make hot Jupiter and warm Neptune very good to test our techniques or test our models. All this are makes it possible, hot Jupiter and warm Neptune make it possible to do very precise observations and basically constrain their properties. So, so the observations that we get, I show you the animation. This is what it really looks like. So on the x-axis you have the wavelength. On here you have transit depth or root of transit depth, root of RP bar system. So here one thing to, this is for one of the first detected planet on which you have an atmosphere HD 209458b. So one thing to note is here, for measuring the transmission spectrum, we need to measure variations of the order of 10⁻⁴ in transit depth. And that is the reason why transmission spectroscopy is so challenging. Earlier, when we were calculating the number of transit depth, this is of the variations in this, because each of these represents a feature of the gases that are present in the planet's atmosphere. And they are of the order of 10⁻⁴. If you just take the square of this and take the difference between them, this is the number you will arrive at. So that small variations to measure using a telescope, you need very, very high, basically have sufficient SNR to do that. And that is why transmission spectroscopy is so challenging. Okay, so here I have just shown you the observations, means how the real observations look like. Now I'll start going into the depth of how we use models and develop models to interpret these observations. So when like I was showing the transmission spectrum, so the geometry that the incident radiation, the radiation travels is this. So essentially I0, basically suppose this is your star here, this is the radiation that is coming from the limb. Imagine that diagram I was showing earlier, and this is how it gets out of the planet's atmosphere. So basically it goes through the planet's limb, and the remnant radiation is basically what we collect at the telescopes here on Earth, maybe ground-based Earth. So basically this beam of radiation is interacting with the whole atmosphere, which includes its pressure, temperature, structure, all the different gases that are present in the atmosphere. So this is the geometry that exists for transmission spectra. I'll go into more details of this further. Similarly, for the emission spectrum, now in the transmission spectrum, we were looking at the limb, and we were getting only the information of this limb of the planet, and the radiation was going like this to the limb geometry. But in the emission spectrum, the geometry is a bit different. So basically, the emission spectrum, you are getting the radiation directly coming from the planet. So directly the radiation that is emanating from the planet's atmosphere. So you see, so one calculation you will do in the next slide where we'll see how much difference does it make. So basically, suppose this is your star. So this was the transmission geometry. It had to cover this whole atmosphere. But in the emission, what we are measuring the radiation that is coming from the planet's atmosphere, and that is what we measure. So what does the emission spectrum basically of the planet looks like? So on the transmission spectrum on the y-axis, basically we had RP by R star squared, isn't it? Now emission spectra directly is a measure of the planet's electromagnetic radiation. So if you look at Earth's emission spectrum, this is what it looks like. So what we are measuring, the fundamental quantity, radiance. So this is what, if you see at here, directly if you take a satellite image, to the spectroscopy and look at Earth, this is the spectrum you will get. You can clearly a massive CO2 feature here, ozone feature, all that. So this is what Earth's emission spectra looks like, and what we calculate in terms of radiance. Because we can do this absolute calculation using satellite. But for exoplanets, we are using an indirect method. What we are doing is we are measuring the planet's radiation just before it goes in the secondary eclipse and during the secondary eclipse. So it's a relative measurement. And that's why our this is also relative, the eclipse depth, what we call it as. So that is FP by F star, the flux of the planet relative to that of the star. So this, when we say exoplanet emission spectra, actually mean the eclipse depth of the planet. So this is what the typical observation of the eclipse depth look like. So essentially now, what we have done for transmission spectroscopy, we are getting this, the transit depth in multiple wavelengths, the primary eclipse transit depth in multiple wavelengths. Now the same you need to do, the secondary eclipse depth has to be done in multiple wavelengths. So depending on how much this varies in wavelength, we basically get what's in the planet's day side, basically from the emission spectrum. So you can see in TESS, so TESS is very small satellite. So that's why here it is much less compared to. So when we go to, this is what the JWST quality spectra, emission spectra looks like. So because of JWST, your aperture size is much bigger. So the emission spectra that we get with JWST is much higher SNR compared to the TESS, and we basically get a nice spectrum where you can detect the feature. So, and for that we require models, which I'll come to in some time. So essentially, basically, so I just wanted to give you an understanding of the difference between what the transmission spectra, so transit depth is, and emission spectra, what is eclipse depth. So feel free if there is still not a clarity on that. So I mentioned about the emission geometry. So there is one important thing why both the geometries are very helpful. Okay. So one more quiz. Okay. So how much distance, this is a very simple calculation. Okay. So how much distance in kilometer does the electromagnetic radiation traverse to the planet's atmosphere for transmission and emission spectrum reaching Earth? Meaning, like if I am making the like I want to measure a transmission spectrum of the planet, so basically the radiation will travel this full distance, but in emission it will travel this difference. So how much is the difference? Can you just roughly calculate what are the numbers? What will be this path and what will be this path? And assume the atmosphere 3H means 3 times the scale height. So I'm giving you, it's like 200 kilometers in the here. The atmospheric scale height is 200 kilometers. So the total extent of the atmosphere is 3 times that of the scale height, which is so one thing is, so it should be somewhere basically, so radius without including the atmosphere is basically here 8,000 kilometers. So essentially, so the main takeaway point will be here that so in this geometry, the number you will get a very large value. So in this geometry, it will be how much? In the emission geometry, 600 kilometers. It will be just 600 kilometers, isn't it? And here it will be somewhere around like a big value. It will be like 60, more than, yes. So that massive number, you can see the amount of it has to travel is large. So because of this leads to very important thing, like what we can do with this. So essentially in the transmission geometry, we cannot probe much deeper in the atmosphere, because what will happen is, because it has to probe such a large path length, as you go lower in the atmosphere, basically your planet's atmosphere will become opaque. And in the transmission geometry, you can't probe deeper parts of the atmosphere. But in emission spectra, your radiation itself is emanating, but it has the path length that it has to travel is not much. Therefore, you can get the information even from the deeper parts of the atmosphere. So that is one of the major things that the benefit of using the emission spectra is you can constrain the pressure temperature structure. This is one of the very important quantity of exoplanet atmosphere using emission spectra, but using transmission spectra that may not be possible, because you are only basically probing a very small part of the atmosphere. And the reason is because the path length that you travel is so big in transmission geometry that you cannot go much lower. So that being said, one more thing that I want to take away before I delve into the equations of the modeling is that when we study this exoplanet atmosphere, the wavelength region of the flux of the star and planet is crucial. The difference between them when we model using radiative transfer, because so like let's take example of the sun and the earth. The sun's radiation peaks in basically the visible wavelengths 0.4 to 0.7 micron, while that of earth peaks in 10 micron in the infrared. So we're very well separated. That may not be possible that for all exoplanets that is the case, but for many of them, if you have a planet around like the type of stars and the planet is like 1000 or 2000 kilometers, still they are very well separated. So this separation in wavelengths become very important when we are solving radiative transfer equations for transmission and emission spectrum. So just wanted to make this point, which you might already know that why that. Basically from simple temperature, the temperature of the sun is very, very higher compared to that of the earth. So for exoplanets, we obtain transmission and emission spectra by measuring their transit and eclipse depth, which I have shown now as a function of wavelength. To interpret this spectra, we need radiative transfer mod. And that is what I will now delve into. Until now, I've been just talking about like how do we take the observation, what are eclipse and transit depth, but how do we model them? That is what we'll go into. So what are these radiative transfer model or atmosphere model? So essentially what we have to do is we have to include all the different components that can exist in the planet's atmosphere. Like the best example is for the Earth. So we need to have clouds, how the radiation travels through the planet's atmosphere, if there are aliens or animals, everything you have to fit in there. Everything that can be there in the planet's atmosphere needs to be there. Of course, that's the most ideal model that we would like to have. It should be fully like dynamics and everything. But for exoplanets, we have not reached that stage where such a complex models could be used. So we have started simple, and we are now using, like initially we have started with 1D models. Of course, three-dimensional model exists. So what these models are basically, they're a set of equations that includes like full chemical calculations, radiative transfer, opacities, clouds, dynamics, everything. And we solve this in massive like supercomputers or depending on how the model is optimized for. And that is what we use then to interpret the observations that we get. And this interpretation can be done in multiple ways. We can use forward or retrieval models that I'll come to that in the next part. So what these models are. So specifically for transmission spectrum, we need to understand some basics of radiative transfer to understand it, and that is what we'll go into now. So as the name suggests, in radiative transfer, we understand how energy is transferred or exchanged when electromagnetic radiation interacts with matter, which for us mainly involves the constituents of the planetary atmosphere. So essentially, when we are developing the models for transmission spectrum, then we need to understand the basic radiative transfer, that how light is interacting with the matter in its path. So here, the terminology that I'm using here is like a pencil of radiation traversing a medium. So pencil of radiation, very famous term coined by famous Chandrasekhar in his classic book. So that is what is nicely used, and it is a good intuitive understanding of what we are talking about. So pencil of radiation traversing a medium will be weakened by its interaction with matter. The change in the intensity of the pencil of radiation with intensity I after traversing thickness ds is in the direction of propagation is given by this. So essentially, di lambda is the change in the intensity, and this will be proportional basically to the kappa, or the extinction cross section, the density, and the incoming radiation. And everywhere you see lambda as a subscript, because all these are wavelength dependent quantities. And that is what we'll see for transmission spectrum. When we say spectrum, it's a wavelength dependent quantity. So everything of this is a wavelength dependent quantity. Okay, so how much the radiation actually di lambda, the change in the intensity of the radiation as it goes through the like a block. So in this case, you can think of, to be more intuitive, like a planet layer in the planet's atmosphere. So essentially, so rearranging, basically now what you will get is di lambda by lambda is equal to kappa rho ds. So essentially, we are just rearranging, and if we solve this, essentially for this one, we get I is equal to I naught exponential minus kappa rho d. So essentially, what we are getting. So you might be remembering which law is this? Can you guess? Something similar you might have studied already. Beer-Lambert's law. Yeah, it's resembles that. Is exactly that. It will come in the next slide. So it is the Beer-Lambert's law. So essentially, because see, when we are doing a transmission spectra, you think what we are doing. We want the incoming radiation in the planet's atmosphere and it is outgoing. So we want to measure how much of that radiation is absorbed, scattered, everything that has been done by the planet's atmosphere. And that is what will be imprinted on the outgoing radiation that we'll capture using our telescopes. So essentially, that is why we are invoking the Beer-Lambert's law. So as I'm saying, we are starting with the simplest possible. So this is the simplest possible equation. So I is equal to I naught exponential minus kappa once we solve this. So all the information, I'll reiterate that again later, all this information of the planet's atmosphere is embedded in this kappa and rho term. And that is what we want. Because we want to characterize exoplanet atmosphere, we want what this kappa and rho are about that planet. So that is what we'll try to find out. And assuming that the medium is homogeneous such that kappa lambda is independent of the distance and defining the path length. So suppose this is your path length, so incoming radiation. So this is, so in different geometries, remember, we are not going to just use this for transmission spectrum. The same thing, of course, with more terms will be used for emission spectra. And again, when we want to do self-consistent models, we'll use that. So depending on what geometry. So suppose this is your incoming geometry, the incoming solar radiation, we can use I is equal to S1, which is at the here is equal to incoming times e raised to kappa min. So here what we are doing is basically how much is the incoming and outgoing. So ultimately that is the quantity we need, the outgoing part. And you'll notice where we'll use this. I'll connect this to the transit depth equation in the coming 2-3 slides. So many times while modeling, we only define the thickness of the atmospheric layer, and that is why this conversion has to be done. Because we know many times in the models we define this dz. But actually, the radiation never will travel like straight. It will have its angle of incidence. That's why we go from dz to ds. So the conversion has been used. Okay. So taking this simple form, I is equal to I naught exponential minus kappa. This is what we'll further use. And here the main thing that we have, as I was saying, is this optical depth. Okay. So the kappa rho ds, as I was saying, all the information of the atmosphere is imprinted is basically in this, the kappa rho ds, which is basically the optical depth. And to understand this intuitively, this is a nice image that tells us. So this is high optical depth, low optical depth. So essentially, you experience that many times in big cities. So, okay. So this is what we will now, as we go further, the optical depth calculation actually becomes very important. So that I'll come to in a minute. So as I was saying, like this is basically the Beer-Lambert's law, as you are all mentioned. And one more thing to mention, and we'll use this, since this law involves no directional dependence, it is applicable not only to intensity quantity, but also to the flux density and the flux. Because there is a limitation of time, I have not gone into explaining what is intensity and flux, and I'm assuming that you would have learned that. Like this flux is basically the integrated over the solid angle, and intensity is per unit solid angle. So they are those two quantities. But the Beer-Lambert's law can be used for both, for intensity as well as the flux. Okay, so and from this basically we can get the transmissivity and absorptivity of the atmosphere. Okay, and as I was saying, so all the information of the planet's atmosphere is essentially embedded in this kappa rho d. So that is why it becomes very, very important to calculate or compute this very accurately. And this is where the term opacity comes into it. So what is the meaning of opacity? So the opacity describes how opaque a substance is, how hard it is for radiation to pass through that substance. Opacity depends on the number density of the particles in the atmosphere and the particles absorbing, scattering, and emitting properties, which may in turn depend on temperature, pressure, and frequency. So opacity is one of the most important physical quantity in the atmosphere that affects of the transfer of radiation. So all the underlying processes of photon absorption and emission are hidden in this opacity calculations and computation. So essentially, basically opacity as a whole includes two parts. What are the chemical abundances of the different gases that exist in the atmosphere? So I'm not going to go into the chemistry of it because Liton is going to cover that in 2 days from now. But the other part is their absorption cross section. What is the capability, or what are the capability of different molecules or atoms to absorb radiation or scatter radiation as when they are present in the planet's atmosphere? That is what opacity is about. So here, like I was just shown one example of like as a function of wavelength, this is what the absorption cross sections of different molecules look like. So how do we get this? So all the models, transmission spectra models, emission spectra models that we use for radio transfer, the backbone of all this is this opacity calculation, because they govern if at a particular temperature and pressure, how much a molecule will absorb or emit, and at what wavelength they will absorb or emit. And that is what we measure in the spectrum. And so the calculation of them is very, very important. So just a basic primer, I won't go into the details. So essentially, basically, what we are, these opacities are representing, they are giving us the information of the line transitions, or we are using the line transitions to get those opacities, and which are measured in the labs or calculated using quantum mechanical calculation. So essentially, if depending on the transitions, you can get the wavelength or frequency for a given molecular atom, depending on what is the pressure, temperature, and that will give you the absorption cross section, the pressure and temperature. But here, when I'm showing you this, here the transitions, means which wavelength a particular molecule will absorb or emit, will be governed by this transition, and that is what we use to compute your opacities. So how that is done is basically we use this massive databases we have. So in our model, practically, so there are these three well-known databases. So this first is the Vienna Atomic Line List Data. So this is quite heavily used by people who model stars. Then ExoMol is what has been developed specifically for exoplanets, and this Hytran has been developed essentially for Earth's atmosphere. So these databases are essentially databases of line list. So essentially the transitions that I mentioned, so as a function of different quantum numbers, these transitions are stored in these databases. So these are mainly, this is like fully experimental. This is mainly based on models and combines experiment also. And this, I'm not sure, like maybe they combine both of them. So all these databases have this line list information, like where different molecules will absorb, and and they are tabulated as a function of temperature. And so all our transmission emission spectrum models have to use these databases. So all the backbone of our models are these databases. But we cannot use this directly because they are just line intensities. But real atmosphere has temperature and pressure. So what we have to do is we have to convert this line list into cross sections. And that cross sections depend on what kind of atmosphere we are modeling. So suppose, for example, like in this case, we have to use all the broadening. So for example, if you are modeling a hot Jupiter exoplanet atmosphere, so that will be basically hydrogen and helium dominated. So the pressure broadening that will take into account while computing these opacities will be hydrogen and helium broadened cross sections will compute. The pressure broadening will be computed using hydrogen and helium pressure broadening. Suppose we are modeling an Earth-like planet. So in the Earth-like planet, so the dominant gas is nitrogen. So we have to take pressure broadening due to nitrogen into account. But Hytran provides something called air broadening, so that is also taken into account. So that basically differs. So that's why when we model different kinds of exoplanets, different kind of broadening parameters, so pressure broadening parameters have to taken into account. And these actually calculations from going from line list to absorption cross sections are massive. They can take like weeks and months also, depending on if you're using GPU or CPU, because the line list are as a function of temperature. And if you want to calculate for wide range of planetary atmosphere going from like Earth, like at 300 Kelvin to 3000 Kelvin, they are massive. So that's why these are computationally very, very expensive. But this has to be done if you want to use a model for multiple planets. So this is what goes into our opacity calculation. The absorption cross sections. This is what we compute. And so now I have given you the basics of like the Beer-Lambert's law and the opacity. So now we'll see how this model transit depth or transmission spectra using the models can be computed. Okay. So suppose this is, let's take this geometry into account. So this is your star, this is your planet and the planet's atmosphere, and this is your JWST, which is near Earth. So suppose you have a planet which is like has below which you cannot like measure. So R low is basically below which it is completely opaque. Imagine that as like a solid surface. For hot Jupiters that may not be true, but it's a reasonable assumption. And this is suppose your height of your atmosphere, HA, the height of the atmosphere. And this is basically R star, the radius of the star, and basically R low plus HA. If you do the addition of the planet's radius and that of its atmosphere, you get the total radius of the planet. So now, given this nomenclature, I can come back because we'll see the equations now. So essentially now, earlier we have defined what transit depth is. So what was transit depth? It was basically the difference in the flux out of transit flux minus the incoming transit, basically in transit. So the difference between the out and in, so delta F divided by out of transit flux, and all as a function of lambda. So that is what is our transit depth as a function of lambda, or basically the transmission spectrum. So this is what we want, transmission spectrum. That is what we want. So how do we compute them in our model? So first is the out of transit flux. So when suppose the planet is not in front of the star. Okay. So basically now we are in this geometry. So suppose planet is somewhere here. It is not in front of the star. So in that case, so and remember what our measurement is happening at Earth or at JWST, which is near Earth essentially. So the flux. So it is basically the inverse square law. So basically it will be the flux that is this F times R star squared is the flux times the radius of the star that is emanating from the star. And what will be that flux at the distance of Earth? So this is that first term. So the out of transit flux. So this is out of transit now. This is now your baseline going on. Okay. So the out of transit flux basically will be directly the star flux. So now the in transit flux. So now that is the term that we actually gives us the information of the planet. So now this in transit flux has total 3 aspects to it. Okay. So now suppose the planet is now here. Okay. So it is now transiting. So now you'll have essentially 3 components. So one is the star, it's still there. Okay. So that is what the first term is giving us. So this term is basically, even though the planet is in front of the, basically is in transit, in the transit, the star is still there. So that first term is basically the stellar flux during transit. Okay. But in this time, the planet is blocking it. Okay. So the planet is blocking it. So we have to subtract that. And that is what is happening in R star minus R low plus HA square, this term. So we are getting the stellar flux by subtracting the planet flux that is there. So that is what we are doing in the second term. Okay. And basically this is the in-transit flux. So in-transit flux basically has 3 components. This is the first one I have just spoken about. The second term is basically the amount of light that would have filtered through the planet's atmosphere. So, okay, so this is suppose the atmosphere. So some amount of light from the star is filtering out through the planet's atmosphere, and that is what we are capturing using our telescope here. So this is the light going through the planet's atmosphere, and this is that term, essentially. And this again, this term is basically, so FSATM, essentially. The atmospheric term is basically the light. I'm just repeating that for understanding. So the light that will come, suppose in that geometry. So this is that the amount of radiation that is filtered through the planet's atmosphere and going through it. And this depends on basically what is the atmosphere made up of. And here we are assuming just currently one layer. We can improve the complexity. And there is one more term that will come into picture, which I have not written here. Can anyone guess what is that? I told you there are 3 terms when the planet is in transit. So one I have given that one is basically the stellar radiation subtracted from the planet is blocking, so that is gone. So that is one term. And the second is basically the radiation filtering through the planet's atmosphere, and there will be third term. Yeah. Yes, so planet's emission, basically the night side emission if it is tidally locked, or in general planet's emission. So that I am neglected here. So why, when we are doing transmission spectroscopy, initially it is all right if you neglect it. Ideally, you should include that term. But for the sake of derivation, I have just neglected here. So why it is all right? Correct. That is actually correct. So in the geometry is the same. The emission is also towards coming toward. The geometry is the same, but it is because of this reason the emission actually is happening because the planet's emission. I showed you that plot now where the Planck curves were different. The planet's emission and the star's radiation are well separated in wavelengths. But you will, in transmission spectrum, what we are doing, we are actually measuring the stellar radiation going through the planet's atmosphere. So it won't have much of an impact. Yes, if we are doing, if we have like very precise, like JWST have been showing us, then we should include the night side emission. But if you are studying the optical part of it or near infrared, like the near infrared also, it won't make much of an effect. Okay, so that is the third term of the emission. So essentially, by just using this, even these two terms of the radiation filtered to the planet's atmosphere and the star, we obtain basically this form. If you just rearrange that, and finally we obtain the transit depth in this form, where we have neglected the terms HA square by R star square because the planet's atmosphere, HA is very small part of compared to the star, and it would basically be negligible, zero. So if you finally get this form. So now if you look in this form of the equation, you have Fs by Fs star. Okay, so what this reminds you? What can we use here now? So this is basic, no, but from model, anything that from the radiative transfer, we can use it here. What is Fs by? So Fs ATM is basically the light that has filtered through the planet's atmosphere, and Fs star is the incoming. So can you use your Beer-Lambert's law now? That is what we exactly do. So essentially, this will be equal to exponential minus tau. So this is where that connection comes, and this is what we model. So using Beer-Lambert's law, essentially Fs by F star is equal to exponential minus tau, and this is what we basically substitute in this, and we can actually calculate the transmission spectrum or transit depth as a function of wavelength by substituting exponential minus tau. And here, so all information of the atmospheric gases, their absorption cross section, chemical abundances, pressure and temperature, all this is embedded in this tau. So this is essentially, so if you are doing, depending on forward or retrieval model, all the information that we get about the exoplanet, like what are the different gases, what are the abundances of these gases, what's the temperature, even pressure and different quantities, all this we basically get from this tau in the equation. Okay. And note that we have neglected planetary emission and multiple scattering for now in this equation. I have simplified it. And for a for realistic multi-layer atmosphere, this is what it will look like, because here I have assumed just one layer for explaining it. But in the real atmosphere, there is something called impact parameter. So basically the impact parameter is from the center how far you are. So it will determine how far you are from this. So that impact parameter used, which is equivalent to the number of layers that you will have. And essentially, this is the final transit depth model equation that you can get to interpret. So the detailed derivation, you can, anyone is interested more in depth, how to convert intensity and fluxes, that could be seen. Okay, so one more small quiz now. Basically, now here we have a transmission spectrum of one of the planets that have generated using model. And here are the cross sections. So by looking at it, can you say which all molecules are present? There are some obvious ones. So. Water, yes, I had water. Then sodium, yes, clearly see. Lithium, yes. Potassium also, yes. So sodium, lithium, potassium, all these are like, they are very sharp features, so clear to identify. But in the you see this part, all messy. So this is what becomes in the near infrared or mid infrared part. We have one to where JWST and all this probe. There are multiple molecules that have cross section. So why is that the case? Why do we have so many like cross sections in this part? Because in planetary atmospheres, we basically have the temperature. So you have roto vibrational transition. So all these are roto vibrational transition of different molecules that exist. So that's why these all transitions, you see a lot of mess. And that becomes a problem when we start doing the retrieval. Okay, so one more thing. So like until now, I've been just talking about the absorption. So I'll just give a brief primer of the scattering as well. So ideally, it's not just the absorption that is happening. It is the scattering also is happening in the planet's atmosphere. So most of the light that, the basic definition of the scattering, many of you might already know this. So most of the light that reaches our eyes comes not directly from its source, but indirectly through the process of scattering. So I'm able to see you and you are able to see me because of scattering. So all the land, water surfaces, and all that we see, everything that around us scatter radiation. And that is what the basics about the scattering atmospheric. And similarly, the particles in the atmosphere also will scatter. So, and you see all these beautiful colors in the atmosphere. So atmospheric scattering, basically the red color during the sunset, the blue color of the sky, all basically are scattering effects. So basically in the model, so because in the model that we derived, I only told you about the absorption, but we have to also include scattering in them. So just some pretty pictures about the scattering. So scattering is a fundamental physical process associated with light and its interaction with matter. So it occurs at all wavelengths throughout the electromagnetic spectrum. So basically scattering will happen at all wavelengths. So we have to include that in our model. So it's a process by which a particle in the path of the electromagnetic radiation continuously abstracts energy from the incident wave and re-radiates the energy in all directions. Therefore, the particle may be thought as a point source of scattered energy. So this is like the definition of scattering we need. And if you look at our atmosphere, we come across a large number of particles, and all of them have the potential to scatter. So molecules, individual gas molecules, haze, smoke, dust, pollens, cloud droplets, ice crystals, rain, everything basically will scatter radiation. So in our model, what kind of scattering we need to include? So because we are modeling this, so when we are making any model to interpret observations, we need to make our model as close to reality as possible. That is the main aim. So we have to include all the processes that are basically happening in nature. And so we have included absorption, we know that. And that is the main aim when we do want to include the scattering as well. Okay, so basically scattering is classified as elastic and inelastic, which many of you will already know. So, but in the planetary atmosphere, the number of photons that are scattered by elastic scattering process, like Rayleigh scattering, is much, much more than inelastic scattering process like the Raman scattering, where there's a change in the wavelength. And that is why we can safely neglect Raman scattering that is happening. Of course, you can study, people can go and see how does that affect, but the effect of Rayleigh scattering is much, much larger than the Raman scattering. That is why in the planetary atmosphere, we are mainly concerned with elastic scattering, where the wavelength is unchanged with light, and that is why we include Rayleigh scattering in all our models. And this elastic scattering is strongly dependent on the dimensionless size parameter, or 2 pi r by lambda, where r is the radius of the particle and lambda is the wavelength of the incident radiation. And this is what basically becomes important when we want to include scattering in our model. So this is one of the nice slide will give you the primer for how different kind of scattering operate, depending on what are the size of the particles that you encounter and what are the different wavelength range. So when we are modeling or interpreting exoplanet atmosphere observations, we are mainly in the optical and the infrared part of the wavelength. So like for JWST, you can see like 0.5 to like say 28 microns it goes, but most of the atmosphere observations have been restricted to 12 or 15 micron. Of course, in the optical, you are 0.2 to 0.6 micron. So in this region, if you see, so the main thing that to take away from this for x much less than 1, which means that the wavelength of the particles are much smaller than the wavelength of the incident radiation, and that is where the Rayleigh scattering essentially happens. So in our models, essentially, then we have to include the Rayleigh scattering or Rayleigh scattering cross sections. We do that. Now, if x is like equal to 1, or basically the size of the particles and wavelength are almost equivalent, basically what we have to take into account is the Mie scatter. And essentially, this is basically what happens to the clouds. The clouds in the planetary atmosphere, they are Mie scattering in nature. And of course, if the particle size are much more bigger than the wavelength of the incoming radiation, you can safely use geometric optics, the laws of reflection and refraction. But that is not the case when we model planetary atmosphere. We are either in either of these two regimes, and that is what we use. If you see here, the wavelength ranges around 1 micron to 10 micron. So we have Rayleigh scattering due to basically the gases. So the gases that absorb will also do Rayleigh scattering. So we have to include them. And then we have also the mean scattering basically due to clouds. So if you are including clouds in your models, realistically, all the planetary atmospheres that we have seen in our solar system have clouds. For exoplanets, we have just begun to find out. I'll tell you in one or the two slides. So we have to start including mean clouds due to mean scattering. So all this basically, when we include in our models, we get like a complete model. Plus scattering has one more complication, which is it has directional dependence. So I won't go into too much details of it. That makes our model too complicated because it has phase functions. And scattering is not uniform. Like emission will happen in all the direction uniformly, but scattering will have a directional dependence based on what is the refractive index of the particle. So it can be preferably a forward scatterer, and can have a donut-shaped scattering. So there are many different types of scattering that can happen. Okay, so it has a directional dependence, which adds to the which gives the additional complexity. So essentially, if you think of just of the Rayleigh scattering, then the Rayleigh scattering cross section, if you compute it, is inversely proportional to the wavelength to the power 4, and that is what we essentially include in our models, and we see using our model. I am not going to the details of Rayleigh scattering cross sections, how we compute them, so we use them in our models though. And when we do that, this is what, like I showed you a slide earlier, just the observation. So the complete model that includes the transit depth calculation, all the opacities and everything, Rayleigh scattering and the calculation of transit gives you a final transmission spectrum which looks like this. So here, this is like the best fit transmission spectrum to the HD21945D using one of the forward models, and you can clearly see. So that is how we detect different molecules and different processes that are happening in exoplanet atmosphere. Like here, you see the Rayleigh scattering that is happening. So lambda to the power -4 dependence, Rayleigh scattering, what we see. We have a detection of sodium and potassium and water feature. This is using Hubble data. Okay, so this is like old Hubble data pre-JWST era. So we so by fitting basically our models to observations, we interpret them and find what molecules are there, what are the different processes, what the temperature is, and all that. And that all the things that I told about the models, everything goes in this models. Okay, any questions until now here? Yeah, go ahead. Oh, so generally we take the square root of that. So they are both interchangeably used. So it means there is no particular reason for why. That is like just a choice of making the plot. So means you could use transit depth also, or you can just a root of transit depth. Either of them can be used. And in the previous slide, what I was talking about, I showed you a spectral fit. Okay, but so as I was saying, the modeling can be done with two approaches. Like one is you make forward models. So these forward models will have all the information of the physics and chemistry, all the opacities and everything. Opacity need to be there in both of them. Physics and chemistry, you solve them consistently, and you get a spectra, and then you fit that spectra to the observation. So here it is, but in the inverse model, it is reverse. Here you have your observations, and then you run your forward models with some relaxed conditions millions of times, so that you get a best fit to the observation. So you have both the approaches that are possible, like forward modeling or inverse modeling. So we take both the approaches when we model exoplanet atmosphere and interpret them. The reason is, so in this case, suppose you are doing a forward model, we have many restrictions we add, like the conservation of energy, equilibrium chemistry, all these are imposed. You'll understand in some things in the next slide and over the course of time. So these conditions are imposed when we are doing forward model, because they are basically within our domains of our understanding of physics and chemistry here on Earth, and that is what we are applying there. That is how then we do forward models and interpret the observation. But the secondary approach, the inverse modeling approach, rests on the fact that we may not understand all the physics and chemistry that is going on in the planet's atmosphere. So let us just keep it free. And so many of the parameters like abundances and temperature and many other cloud parameters are kept free, and that is how we interpret them. So with JWST, we are realizing that the best approach is to combine both. We cannot, because if you just use inverse model without any restriction, it can go randomly anywhere. How do you know that the constraints that you have get are realistic? So the ideal way is to give both approach and see where they meet. Of course, there are differences that we see, and that is where the challenges are, and we are progressing ahead. But the inverse model, the radio transfer computations have to be done millions of times. That's why the models that we have to develop have to be very fast, so that this retrieval can be done like millions of times as required for the retrieval. So with the JWST era, so in the previous one of the slides, I show you HD209 spectrum using HST data. Now with JWST, with HST, we only had access until 1.7 micron. With JWST, now we have access all the way from 0.5 to like 5 micron beyond until 15 micron. And what this has opened up? This has opened up the arena to discover molecules in this exoplanet atmosphere like CO2, SO2. And the reason the same, I told you, if you look at the absorption cross-section, because of the rotovibrational transitions, many of these molecules have their cross-section in this wavelength region. And that is why we have been able to detect like CO2, SO2, CO, and many, many molecules, methane, and all we have been able to detect in different exoplanets after JWST since like 2020. So this is one of the first initial targets from the early release science program, where we were able to detect H2O, CO2, SO2, CO for the first time in WASP 39b, one of the contributor targets. So the infrared observations of JWST has allowed us this detection of multiple spectral features and features. So does that mean that JWST will solve all our problems? Is that so? So I'll come to that in a minute. One more example what JWST has given us is clouds. So that has been one of the major problems before JWST. Like we only had access to optical data, and we were using like very simplistic clouds. We did not know what kind of clouds exist. So in this one of the first work, we were able to detect actually SiO2, quartz crystal clouds, because many of the cloud, if you see the cloud cross section or the mean scattering cross sections for different clouds, they lie in basically this beyond 5 to 12 or 5 to 15 micron, their features. So without JWST, we would not have been able to detect the clouds that are present in exoplanet atmosphere. So here in this case, the SiO2 cloud detection has been possible because of the JWST, and this is using the MIRI data, the MIRI instrument data. So JWST has made possible all this detection of multiple molecules, clouds, but has it solved all the problems? So JWST observations are revealing abundance constraints of various species are quite sensitive to model choices. Therefore, more observations or transits to obtain high SNR, large wavelength coverage with detailed models are needed. So even with JWST, we have. So what was happening is earlier our models were very good, but our data was very bad with HST. So we were getting very good constraints, everything. So we thought our models are like the best. Then JWST data came in, and when we started applying our models, we started seeing, oh no, that our models are not fully ready. So it's like the process is a feedback in itself. And the one example of this is also like what we are seeing. This is one of the recent work where we found out that even with JWST, we cannot get accurate constraints on the abundances of the different species, because in this, this is for same HD20945B, this was just using HST, and this is JWST. So when we apply our retrieval techniques, we find that the constraints on the abundances of the molecules that are like easily detected, CO2 and H2O, differ by almost 3 orders of magnitude if we just use JWST data compared to when we combine with HST, the optical data. So this has actually very big implications that with JWST, we cannot get accurate constraints on the abundances of the different species in all the different planets that we are studying. And we need optical data. So this has much implications for the NLOT and EXO worlds, because we will have access to the optical data, and that we basically for the JWST targets that we have studied, by combining both the infrared and optical, we get a more robust understanding and estimate of the abundances of in various exoplanet atmosphere. Okay, so basically that's why JWST is very good, but it is not solving all our problems, because it was never designed for studying exoplanets also. One of the things, so we have to leverage other facilities that we are developing, or think of new ideas of how we can constrain the atmospheres of these planets better. The other challenge, which I'm particularly very, very interested in, that is what we were discussing earlier also, terrestrial planets. Now with JWST, you see flat spectra, essentially. Sourav was mentioning this in the morning. So because if you think about the transit depth and the scale height, so if you start studying the transit terrestrial exoplanets, the scale of the height of the atmosphere is so low that your SNR is not enough that you will get any features. Like if you have a nitrogen dominated atmosphere or CO2 dominated atmosphere, and that we are seeing here. TRAPPIST-1E was given JWST time, and we studied them. And in that case, basically, no definitive confirmation or ruling out of the possible atmosphere. So the paper says that there might be an atmosphere. We are not getting any certain constraints on the atmosphere. So what it is telling us, even with JWST, it is proving very, very difficult. And remember, this is a terrestrial exoplanet or an M dwarf. If we start thinking about terrestrial exoplanet or on G-type stars or like sun-like stars, then there's no chance we can do it. So that's why we have to start thinking about like how can we characterize these terrestrial planets using current or future facilities. So with JWST, it seems that it will be very, very challenging. So essentially, as we go from like, so in the initial HST and JWST phase, we have been studying hot Jupiter and exo Neptune and super Earth. So these have been our primary targets, and the observations that we are getting from JWST are excellent. And so they are a very good test for what we understand, what we don't understand for our models, and we are able to get. But as we go to smaller and smaller planets or lower and lower mass, it becomes very, very challenging to characterize them. And that is where the challenges lie ahead in terms of like instrumentation, modeling, observations, all of them to characterize this. And so the question that Sourav was asking in the morning, what can we do with NLO2 to address this? So the instruments, people can start thinking. I definitely am going to start thinking, like what can we do with NLOT to characterize terrestrial planets? Okay, so I know I'm short of time, so I'll briefly go through it. And so I have been speaking about the transmission spectra a lot, but as I said, the transmission spectra does not give us the full information of the planet. What we need is the emission spectra as well, especially to constrain the pressure, temperature, structure. And it is very, very important to constrain that because that structure basically gives the overall how the atmosphere is like, which I'll like for Earth, we have like troposphere, stratosphere, and that governs the overall dynamics of the planet on how it is like. So as I was saying, in the transmission, you're looking in this geometry. In emission, we are now basically have the geometry where the flux is emanating from the planet itself. So so basically, you're taking the measurement here, and you're on the day side, suppose it is tidally logged, you're getting the radiation from the planet to calculate, basically obtain the eclipse depths. And again, just reminding you all, basically the emission from the planet now will be basically in the infrared regime, while in the transmission spectrum, it was in the optical regime because that is where the stars emit. So that being said, so the earlier equation that we derived for the Beer-Lambert's law, in that we did not include any emission term. We neglected it. But when we want to get the emission spectrum of the planet, we cannot neglect that because that is our primary signal actually. So the radiation that is emanating from the planet, it is emitting. Of course, on the way it is getting absorbed. So that is this term takes care of that. But each of the layer of the atmosphere is emitting. That's why in our equation, we have to add this, the B or the emission term. So we add this emission term to that pencil of radiation that we call it as. And this is what is the Schwarzschild equation. That is what in the radiative transfer, what we call it as. Of course, one thing I'm like specifically mentioning here is it is a non-scattering medium in LT. So we have assumed that there is no scattering happening when the Schwarzschild equation and LT, that local thermodynamic equilibrium exists. So that is only in that condition we will be able to use it. That is fairly good because most of the planet's atmosphere is contained in the region when local thermodynamic equilibrium exists, which is the number of collisions are much, much more than the radiative transition. So ultimately, this is the form of equation then we are going to solve to get our emission spectrum. So again, the same, if you see here, to solve this, we have to again use the optical depth as we defined earlier, kappa rho ds. And essentially, we are now, so earlier we only had this di by d tau is equal to minus I lambda. We have now this b lambda term. So the radiation is coming from here. It is getting absorbed, and but the layers are also emitting. So in simple words, if we want to think about the planet's atmosphere, then what is happening here is there is, suppose this is the base of the planet. So each of the layers is now emitting. And each of the layer is interacting with each other. And what we are measuring is the radiation that is coming at the top of the atmosphere. That is what we are measuring. And that essentially is embedded in the Planck. So once we solve this, so essentially we need to solve that Schwarzschild equation, which is basically gives in this format. So I is equal to I naught exponential minus tau. Okay, and B lambda E exponential minus tau. So essentially, so here you can think of the radiation from this part. So this is I naught initially will come. It will be absorbed in this layer. That is what the first term is about. But then this layer itself will again emit. So that all has to be done like iteratively. We have to do that, and that is what we do in our models. We iteratively solve this for multiple layers, for starting from the bottom, where the radiation from the bottom layer will be absorbed by this. It itself will emit. Again, it will be absorbed, emit. So all this will be iteratively done. Finally, the aim is to get the emission at the top of the atmosphere as a function of, again, everything is as a function of wavelength. So that is how you then get basically the flux at the top of the atmosphere as a function of wavelength, or basically the emission spectra. Okay, but here one thing to notice that I have written here is like, suppose you are considering this is the input. So then you have to traverse your basically the optical depth is full. But if this layer is emitting, then it only has to travel this layer. So that's why when you integrate the B term, it's S1 to S, not from here to. That is what is mentioned. Of course, you come to me and to discuss. I know there are a lot of equations there, so we can discuss in depth about this. Now, so including the scattering source function. So generally, when we are computing the emission spectra, we don't use it. But if you want to go to reflection spectra, then the scattering source function becomes very important, because scattering, ultimately there is no change in the wavelength, and it is basically the incoming light that is scattered. So when we are want to model the reflectance spectra of the model, the scattering term actually overtakes emission term. So depends on what you want to model, different terms are used. So I won't go into the details of it. So primarily this is what the final equation looks like. So this is what the emission spectrum of one of the hot Jupiter targets, just an example I'm showing here. This is what the eclipse depth and the wavelength. So this is like the carbon dioxide feature in eclipse. So this is only possible because of JWST. Okay, so the precision is sufficient enough that in eclipse we can get the eclipse depth to get a feature. So in this case, what is happening is basically you have a pressure temperature structure of the atmosphere. So the radiation is coming from these layers. There is CO2 in between, and this CO2 is absorbing radiation, and that CO2 is basically seen as absorption feature. And that is what we are measuring. So basically, we are measuring directly the CO2 in the planet's atmosphere using that emission spectrum. Similarly, this is also there is not apparent. This is the water feature. So, so these molecules like water, CO2 can be detected in the eclipse spectra of hot Jupiters with JWST. Okay, but what if we come to terrestrial planets? So again, so this is one of the very interesting study and very so for 55 Cancri E, they actually managed to get a emission spectrum for terrestrial planets, but the reason was it was very high temperature. So why that is the case? We are only able to. Why am I saying that we are only able to get for high temperature? What if this planet would have been like 400 Kelvin or 500 Kelvin? Yeah, because if you see as the Schwarzschild equation, the B term, it depends on the temperature. So if you're here, the temperature is lower, 300, 400 Kelvin, the signal, the number of photons that we get will be much, much lower. So the SNR is not enough. So that's why characterizing low temperature planets using emission spectra will like, it's not even, I mean, correct me if I'm wrong, but I don't think it will be possible with JWST. We can characterize the high temperature terrestrial planets that we see here, but low temperature, because like in emission spectrum, the capability means if we can characterize a planet depends highly on the temperature. Like if a planet can be characterized in emission spectrum, heavily depends on the temperature. It's not just the scale height that matters. For transmission spectrum, it's the scale height, but in this case, the temperature matters. Okay, so I think that the time, because I want to keep some time for questions, and so this part I'll then just so one more thing I wanted to cover, but actually it will be quite involved. Basically, I'll just give a primer for that. Is in the previous slide, I have just spoken about the emission and transmission spectra of the planets and how do we model them and interpret and use those models to interpret this observation and constrain the abundances and pressure temperature structure and all that in the planet's atmosphere. But how do we model the planet from first principles? Is there like for example, if you want to compute a transmission spectrum or emission spectrum of the planet, we need to assume a pressure, temperature, structure of the planet. So where will that come in the first place from? How will we get that? Any guesses? Anyone can answer means, yeah. Because no, that is self-consistent way. Yes, that is one way. That is what I'm talking about. What are the other ways? Suppose I'm doing an inverse model or retrieval model to basically interpret those observations. So what can be done? So known pressure, temperature, structure. But for exoplanets, that's the problem. We don't know anything. But that's the thing. So for Earth, if you see the pressure, temperature, structure, we have starts at 300 Kelvin. Imagine if we use this for hot Jupiter, we'll be totally wrong. Yes, correct. Yeah, no. So my question was basically like if you're modeling exoplanets, different atmospheres, like maybe hot Jupiter or super Earth. So how will which pressure, temperature, structure I will use, or how will I get that? Yes. So basically, yes. So that is one way, and what you mentioned second. So there are two ways to do that. So if you're doing an inverse modeling, people have developed parameterizations to do that using like basic derivation. They have done parameterization, so you can keep your pressure, temperature, structure to be free, and do the inverse modeling. And so when you fit to your emission spectra, you will get what will be the pressure, temperature, or structure of the planet. Yeah. Yeah. No, we correct. Yes. But that will be parametric still, because it's we are changing that parameters. We are not changing the means that parameter is changing the PT, and then that is going in. So exactly. So that will be the problem. Like, how do we constrain the range? So that is where the same problem comes into picture. Like, how do you like you have one approach of inverse modeling and then forward modeling. So how do you say which one is right? So that's why we have to combine both them. So your retrieval is giving one pressure, temperature, structure. So the other way, what you mentioned is like you have to generate pressure, temperature, structure from first principles, or what we call as forward modeling. So this is what we have for the Earth. Okay. Now this is a complicated PT profile, but over the years, like in the 60s or 70s, people managed to produce this using models, and they got Nobel Prize for that, the radiative convective profile that they made for it. Similarly, if you want to get the estimate of this from first principles, then again the same means I wanted to motivate that we have to solve the radiative transfer equation in this geometry again, where you have multiple layers now. Sorry, multiple layers, and you have to solve for all the radiation that is incoming. It is being like absorbed by the atmosphere, then re-emitted back. So all scattering, emission, all the processes have to happen. And one more thing that you have to compute it, like when we are computing the transmission or emission spectrum, we are only bothered about like how much it is absorbing, or basically is it giving a feature like a transmission in the absorption feature or the emission feature. How is it related to the temperature? But in this case, we want to actually compute how much of the energy is being dumped in that particular layer and how much energy that layer is losing. So all that energy balance has to be taken into account. The absorption, scattering in each layer, and how much it is emitting. So as I was saying, the radiative transfer that we use for transmission spectra model is different from that we use in emission spectra model. And again, if you want to do this self-consistent calculation, it is again different. And that is what I wanted to touch upon. So I'll just briefly go through it. So that is, so how do you model exoplanet atmosphere from first principle? You get the first estimate of that, like what will be the pressure, temperature, structure like. The input will basically be, because only we have some basic information, like how far the planet is from its host star. You only have that information. Of course, the radius and mass of the planet we have. So from all those information, how do you get that? So that is where the detailed models come into picture. But before that, so if you want to get a rough estimate of that, so the equilibrium temperature is that temperature. So if you use the equilibrium temperature, we get a rough estimate of what the temperature of the planet will be. But it's like very crude. Because if you calculate for Earth, we know it's 255 Kelvin, but here we see it's 288 Kelvin. So this is what we call it a zeroth order model for Earth's energy balance. Because what we are energy, the balance is the incoming radiation from the planet, from the star on the planet, and outgoing radiation. To balance this simply, we get the equilibrium temperature of the planet, which is essentially the energy, Earth's energy balance, zeroth order level. But if you want to go into the details, this is the kind of setup that we have to use. You have to solve the radiative transfer equations like this. The full incoming radiation is getting absorbed, scattered, and then it is re-emitted back. You have to balance that. You have to include chemistry, because you, as I was saying, in opacities, you need to calculate the number density, what your atmosphere is made up of. That also we don't know. So how do we get that? That is where chemistry comes into picture. I won't go into details of that. Liton will talk about that on Friday. Compute opacities. I have mentioned that. So because your opacities are temperature and pressure dependent. So suppose you are calculating, so this is a very, that's why these computations are very computationally expensive, because suppose you are calculating using radiative transfer this PT profile. So you will compute opacities for that in one iteration. But in the next iteration now, your PT has changed. You'll have to again compute that. So this is a very heavy computation. Iteratively, you have to solve the radiative transfer equation, chemistry, opacities, all of that. All of that will be solved ultimately to get a pressure temperature profile that gives you basically under the constraints of conservation of energy and hydrostatic equilibrium. So basically the energy from each layer has to be balanced, and overall atmosphere has to be balanced. So I'm just finishing. So essentially, this is the kind of PT profile that, so basically that is the first order or a self-consistent estimate of what is the pressure temperature structure of the planet like. Of course, there are some assumptions going into that, but if you make them reasonably, then they can be valid. And that is why we need to combine both forward models and retrievals to get a holistic understanding of the exoplanet atmosphere. Okay, so there are these equations which I would skip now. So essentially, this is kind of basically that I was talking about the Nobel Prize winning work. So they managed to get the Earth's temperature profile by solving these equations. Same concept we are applying now, but now the challenge is that we don't know anything. The chemistry is not known. We don't know anything what the planet is made up of. We don't know the temperature. So that is why it becomes a more challenge. And I have only talked about the radiative transfer part. The convection also has to be included if we are modeling terrestrial planets. Okay. So with that, I'll just end here. General take-home messages, simple points. You can read this, and I will be happy to take a few questions or discuss later in more details, because I've covered many equations I need. Thank you very much. Yeah. Yes. Hmm. Yes. So that's a very good question. So that is currently so there are various ways we can resolve this degeneracy. So one basically is, like suppose, for example, you measure an H2O feature, you get a particular abundance. So, but you have to make sure that that abundance also is valid across all the different wavelengths. So if you have multiple features of that across different wavelengths, then you will be able to constrain it accurately. Meaning, if you have large wavelength coverage, then you can get rid of this degeneracies in constraining the abundance. But so this is case of abundance. Then again, for the pressure temperature structure, there might be any other like way to consider. Like if you have an inversion in the planet's atmosphere, all your features will have to be have inverted, because that is what the temperature structure will be like. So again, the wavelength coverage with many more molecules will be able to remove that degeneracy. So that is just one example of how we can remove degeneracy. But that is true, like it's a major problem in the field. Like how do you resolve all the degeneracy? But that is like the part and parcel of the things that we do. It will come, and we have to think of the different ways to resolve it. Mm. No, but if you increase the wavelength coverage, why your parameters will change? Oh, you're saying the more molecules will increase. But there will be certain molecules which will have more transitions or more absorption bands. There will be certain molecules that will have less. So that we cannot do. So certain molecules will be able to remove the degeneracies. Like for that famous K218, initially we thought it was like what, water rich, then it became methane. So because we had more wavelength coverage, we were able to anchor it. So that is how it can we will be able to do that. So the parameters won't change much. We'll increase the number of molecules because it might have cross section there, and then we can do that. So, but there we'll have to try many other possibilities in our retrievals and see which gives us the best fit to that. Does that answer your question? So yeah. Okay. Hmm. Yeah. So the mean scattering basically calculation. So mean scattering basically, if you see, they are the analytical solutions to the Maxwell's equation. So we have the numerically the analytical solution for that. So if you solve that, essentially you will get the cross sections, the directional dependent of those, and the cross sections for different kind of species. And some of them have been experimentally also people have tested for some of the species, but I cannot say that for all the species people would have tested. But for some of them, they have been experimentally varied, like especially which are important for Earth, like sea salt or black carbon and all that. They have been very experimentally people have verified. That was your question. Yeah. Hmm. Correct. Oh, so you are saying that if there are clouds present in the planet's atmosphere, yes, or they're obstructing more light in. Yeah, yeah. So definitely, yeah, that becomes very important, especially polarization, which Sujan might have spoken yesterday. That actually is a very strong technique to do that. The problem is our current SNR that we get for exoplanet observation, even with JWST, we cannot do polarization. First of all, SNR is not sufficient enough to do polarization. So you need a bigger aperture size. Maybe with ELT or like with NOT, people can try. That is one way we can get that directional, because the knee scattering particles, they have very different degree of polarization depending on how you are looking at it. Okay, so and I think on this Venus mission we have one polarimeter instrument, so there also we will be able to see how the Venus clouds affect. Yeah, yeah. Hmm. Hmm. Uh, hmm. Hmm. Yeah. So, so for your first question, so why we need to study this thing? Secondary eclipse is, so in this plot, we are seeing the secondary eclipse is very small. This is what you are referring to. But see, the secondary eclipse is all the valuable information about the pressure temperature profile of the planet. That is the most strong reason for studying the emission spectra. Because as I was saying, in transmission spectra, you don't probe deeper parts of the atmosphere. So essentially, that I was showing in that plot, maybe you'll remember that. So you cannot probe much deeper in the planet's atmosphere. You probe a very small part of it. So you cannot get the information of the pressure temperature. So the only way we can do that is the emission spectra. One is that. Second is, if you are studying like tidally locked planets, then you will only get the information of the day side from the emission spectra. From the transmission spectra, you cannot do. So those are the two strong reasons that why we need to study the emission spectra, to get the more deeper, full the atmospheric understanding, and also the day side of the planet's atmosphere. Yeah, so again, so the question what Priyanka was asking, the degeneracy will come in. You take any PT profile, you will get similar transmission spectrum. But if you take different PT profiles, you will get a different emission spectrum. So that is where the difference lies. How much the PT profile will make the difference in the in your transmission, in your emission spectra, that matters. Like for example, this is the classic. So suppose you have a pressure temperature profile which is like this. I hope you are able to see this. So this is a non-inverted pressure temperature profile. Similarly, you can have a pressure temperature that is inverted. So they will have different signatures in the emission. Like in this case, it will be an absorption feature. Okay, and if it is inverted, it will be an emission feature that we'll basically get. So that is how we'll be able to differentiate between an inverted and non-inverted PT profile, and that is how we were able to discover one like stratosphere in one of the planets. So that is using the emission spectra, because it leads to differences in this one. But now, if you do the emission spectra, transmission spectra, using both these PT, the effect on the transmission spectra will be very less, negligible. So that's still an open question. Like with HST, I can be sure that this won't give you with the transmission spectra that we get from HST, we cannot differentiate between these two PT. It will be like both can give same transmission spectra. With JWST, people are thinking, and it's still challenging. It's not we can because one of the main reasons in transmission spectra, you probe a very small part of the atmosphere. So already you are missing the information of the lower part. You're getting very small part of the atmosphere, and basically your spectra is only affected by the temperature in that region. And the second question also I answered. Okay. Yes. Yes. Yeah, so this is basically, if I remember correctly, those are the Miri wavelengths. So in the Miri wavelengths, that is what generally we are so 2000 Kelvin. And the other reason is basically, if you see the Planck curve, so this is your number of photons already are very less in that area. So that's why your error bar tend to increase, because the peak of like 2000 Kelvin will come around, I don't know where, 4-5 microns or something like that. So both the reasons combined, the Miri plus also the less reduced number of photons that might have contributed to that the large error bars that we see here. So only thing that they have fitted these different models, and they are able to say that it might be a CO2 or I think N2 dominated atmosphere that only can fit this part. From this part, we are not getting any like viable. This is the part that is constraining. But this was like the first terrestrial planet in a sense they were able to get the emission spectra. But because of its high temperature, we got it. So that is the main. Any more questions? Anyone have? Okay, it's the tea time, is it? Sorry to take the tea time. Yeah. Oh, the CIA, the collision induced absorption. Okay, so that's a good point. So essentially the collision induced absorption. So what she's asking is a very important question. So collision induced absorption is basically the absorption due to the dominant gases. Basically, like if it is hydrogen, helium, or for Earth, nitrogen. So in transmission spectra, they are setting the continuum. So that is what this continuum is set by the CIAs. So actually, the better plot is this. Where is the cross section? Yeah. So if you see the H2 and He, this two, this is the H2 cross section, and this one H2 He. So they are basically setting the continuum where the base of that transmission spectra lies. So they are very, very important because they are giving you the base of the transmission. So question is basically for emission spectrum where they become important. So in basically for emission spectrum, they will important because they will lead to absorption. So when we are solving a radiative transfer equation, so depending on the collision induced absorption, they will absorb the radiation. So essentially, they will also play a role in setting your continuum for the emission spectra. So in a sense, but we cannot clearly see them. So I don't have a plot here. So if like similar to the absorption process, if we decouple the emission spectrum in different based on different opacities, then we will be able to see that. So they will help setting the continuum even for emission spectra. Yes. So that is debatable. People have started keeping it free if the mass is not known for like young planets. Yeah. So we have seen that when we actually keep it free, then we are able to get some of the constraints if we don't have a strong constraint from the radial velocity. Because there have been papers which have said, like one from Sarasigar, them that you can constrain the mass of the planet using the transmission spectrum, but there have been papers refuting that it cannot be done. There are many more degeneracy. So I think more understanding with the GWC data might help that. So it can go both ways. Yeah. Yes. So actually means ideally if it is not even gravitationally locked, you should be able to see it because tidally locked, because what we are measuring is when the planet is star plus planet. So if the planet has a sufficient temperature enough, it is emitting some radiation. So anything that is it will be added. So your baseline essentially goes up compared to when it is in eclipse, when the planet is not there. So it's the difference in that planet plus star and just the star that gives us the secondary eclipse depth. So if the planet has a temperature, basically it will have some temperature, then it will, even if it is not tidally locked, there will be a secondary eclipse depth. So that totally depends on the temperature of the planet. That will govern that. Yeah, depth will change, yes. Yeah, so ideally, if you can think, I mean, if I assume that I have like sufficient SNR, massive telescope, so the emission spectrum actually you can it will change, and with each phase it will change because you can always measure at each different phases. You can measure the planet plus star and subtract from what it is an eclipse. So at each phase you can have a different emission spectrum. So actually we have got that with JWST for WASP 121b, one of the ultra hot Jupiter, which a very high SNR. So we have got at each phase we have been able to get emission spectrum. So it will change the eclipse depth changes, and that also changes as a function of wavelength. So it can give us the information how the dynamics of the planet is happening. That is very valuable information.